what we found was we had technology shifts where some technology couldn't talk to older technology. And this caused some problems, especially in industries that had adopted technologies that could not take massive change because they were more worried about reliability than being on the bleeding edge of things. So your operational technology organizations, where I've got a controller that's running pumps on a dam or gates on a dam, I can't just willy-nilly put the latest and greatest on there if it hasn't been tested. Welcome to Embracing Digital Transformation, where we investigate effective change leveraging people, process, and technology. This is Darren Pulsipher, Chief Solution Architect, author, and most importantly, your host. On today's episode, the history of data-centric application development with me, your host. Hey, I decided that it was time to redo episode 1. Episode 1 was 185 episodes ago. I can't believe it's been that long. But I went back and looked at it. The information's interesting. I need to update the information. But more importantly, oh my goodness, the production on it was horrible. So I decided it's time to redo it. We can do a lot better job. So let's dive right into the history of this. First off, before we talk about the history, I want to first talk about why we're talking about it. Gen AI has really kicked off an amazing run on data, and it's really changing fundamentally the way people work, much like the internet did in the 1990s. So we're at a pivotal point where things are changing. We just came out of a pandemic. Gen AI comes in. Edge technology was going before that, and it made a big impact on the amount of data that we're generating. So the two together, Gen AI and Edge, they're creating a big, huge wave with really huge implications on, frankly, the amount of data that's being generated and how much we're just leaving behind. It also has increased the security attack surface dramatically. There's a lot going on here. But before we go into all that, let's dive right into what happened when we first started. When we first started doing application development, it was pretty simple. I had data that I focused on that I wanted to convert into something else. If I go back and look at the ENIAC, or I look at Turing's machine that he set up to break the Enigma, it was all about data being moved from one format to another. So the basic building blocks that we had to do that were I had a machine that I would give it data, and I had an application that would transform the data and spit it out into some kind of storage device, whether it was cards or ended up being magnetic tape or drives that we have, and a lot of technology changes in the way that we stored things. But ultimately, what was on that storage was data that I needed. So I had data that I put into an application and would come back out. We had these purpose-built machines that did very specific things. We came up with more general machines when central processing units came out. But the basics were the same. I had a central processing unit and I had storage. And then network came into play. DARPANET was set up. ARPANET was set up. And then in the 1990s, networking just went hog wild crazy. The internet started just connecting. And I started connecting these purpose-built devices via network, and these more generalized devices via network, and they can talk to each other and share data across with each other. And this is how things went in the 90s for some time. And it was actually pretty good. So a lot of really cool applications were developed. I could share data between machines. It was great. Now, here's some downsides to it. It took a long time to develop new applications. I wasn't really reusing technology very well, because applications were built for specific hardware. And then technology started moving really fast. Moore's Law was kicking in the 70s and 80s and 90s and 2000s, where the density of transistors were doubling every 2 years or every 18 months, depending on where we were on the curve. Very crazy technology going everywhere, right? And then what we found was we had technology shifts where some technology couldn't talk to older technology. And this caused some problems, especially in industries that had adopted technologies that could not take massive change because they were more worried about reliability than being on the bleeding edge of things. So your operational technology organizations, where I've got a controller that's running pumps on a dam or gates on a dam, I can't just willy-nilly put the latest and greatest on there if it hasn't been tested. Right? I can't do upgrades all the time, technology upgrades, because the cost is too high for loss of life if something happens that goes wrong. So we started seeing these technology drifts specifically between the operational technology side of the house and your IT side of the house, where I could take some downtime. Now, lives weren't lost if downtime happened, a lot of times in the IT realm. Costs actually increased dramatically. These machines were expensive, and developing on these machines was expensive too. So I had to work through those sorts of things. In the 1990s and 2000s, we saw the birth of something called virtualization. Now, what virtualization did, and it actually, there were inklings of that even before that in mainframes in the 70s and 80s, but virtual machines really came to play in the 90s and early 2000s, where I was able to virtualize my machine. I could take that machine and I could create it onto a piece of data, that I could take that data and now move it to other machines, and it would come up and run where I stopped. I could snapshot virtual machines. It was super cool, right? Because now I could tie my application to a specific operating system, and I could run that on any machine that I had, right? As long as it had a CPU and a drive. Now, what made this even more portable, there were some problems with it. It wasn't completely portable, but what made it portable was the birth of Linux. Because what Linux did was something really interesting. Linux created a Unix-based operating system, which were running all of the data centers at the time in the 90s. And all the data centers running in the 90s were proprietary operating systems for proprietary hardware. Sun had Sun OS and Solaris. IBM had AIX. HP had HPUX, and they were very good operating systems tied specifically to the hardware underneath, the CPUs and the network that was now in there and all that. Linux said, I can run Unix on any x86 processor. Now, x86 was not really in the data center. They were on people's laptops and desktops and things like that. But you had all these sysadmins going like, yeah, this is awesome. I can run Unix on my laptop. I can run it on my desktop. I can do a lot of things. And it's a whole lot cheaper to buy a desktop than it is a high-end server. And Intel took advantage of that with Linux and started creating data center SKUs that were running x86. Very cool. Lower cost and more pervasive. And then virtual machines could be ported across multiple vendors. They broke down some barriers to entry, and now more people could enter into this space. Major adjustment to the industry. People said virtualization will kill the CPU market. It did not. It did not at all. In fact, it created more consumption because people could more easily develop applications and they could be moved anywhere. Not only did we virtualize machines, we also virtualize storage now. And we also virtualized networking. So we made it even easier to add new applications and new types of new types of data in my storage and new ways of connecting things together. And this was pretty cool, right? This made it more portable. I could do things faster at a decreased cost, but it came at a cost. The cost that it came at was security. Because now my application and data could be put into one blob that could be now moved around anywhere which meant an increased attack surface, and someone could grab my application and the data and the security keys, all that stuff together in one blob and put it on a USB key and walk out of my data center, and I would never even know. That's kind of scary, a little bit scary. Another cost that came with this was something we call noisy neighbors, because a virtual machine, I can have multiple virtual machines running on the same piece of hardware, which means that they affect each other, both in I/O and CPU and memory usage, all these sorts of things. So I now had to start monitoring noisy neighbors, and my predictability on performance kind of went down. Before, I knew exactly how long something would take when I ran it on the mainframe, and I had the whole mainframe to myself, right? I knew exactly how long it would take. It would take within, 1 or 2%. Now, noisy neighbor can introduce a lot, like 5, 10, 20% performance variability, which, wow, that's a lot. That's a lot to worry about. So those are some downsides to that. So what we saw continual progression. The progression that we saw next was cloud technology. Now, cloud technology came out of a group that were doing grid technology. Now, grid technology, this is not electric grids. This is grid technology that we saw in high-performance computing, mostly out of the national labs. And this is when I can tie a whole bunch of machines together, and they look like one big pool of resources that instead of saying I want to run one VM, I submit jobs to it. And the jobs get dispersed across all these machines that look like one big pool of resources, and storage is available everywhere. And the whole idea is that we made it simple to deploy applications. So we abstracted away the need for, hey, I've got to have storage and network and machines of a certain OS. All that got abstracted away in cloud. And I made it easy to set up these pools and things like that. That led into cloud technology, which improved on that abstraction even more, which made it easy for me to go to a website and say, I need 5 really large machines. And you weren't getting the whole machine. You were using VMs on those machines. So this came out of a necessity that organizations had to, hey, I need more capacity, but I don't want to spend all my cost on CapEx, on buying new hardware. And so that was the big movement in the early 2000s. And there were several different business models that were being used at the time. And the two contrasting ones were coming out of the HPC world, where you normally spent money on these big HPC clusters based off of CPU time. How much of the CPU clock time were you using? And that model was very traditional in high performance computing because it came out of the mainframe world where you're paying for a CPU clock time. Amazon came up with an interesting model, which made it a viable business model to move forward, which was not CPU time. It was wall clock time, which meant if I had a job running for an hour, it cost me $1.50 or $2 or whatever, regardless of how much CPU cycles I used. Because what they found was, hey, the CPU cycles aren't nearly as important as how much data is moving through the CPU. So they came up with a simple way to understand. I pay for how long my VM is running. Highly predictable, much more predictable than the old model. So people glommed onto it, especially developers, where they said, hey, I need some more resources to test or to simulate something. And Amazon has some spare cycles in their data center because they don't need their whole data center capacity for most of the year, only the last 2 months of the year. Amazon starts renting out cycles, and it becomes highly profitable. Other organizations glom on, Azure, Google, start doing the same thing. And we even have regional cloud service providers that are popping up. The key aspect here on the technology side is the ease of use, a single portal to now provision hardware or virtual hardware, right? Before, what would happen is I would have to come up with a big plan. It would have to be approved by my IT. IT would go through procurement, and the process took months. With cloud technology, I could spin up more capacity in minutes, which is incredible, right? I lower the barrier to entry again. Now, some really interesting things with this. You would think that, oh, this is going to kill the data center. This is going to kill CPUs. Oh, just the opposite. Just like before with virtualization, it increased. How can that be, Darren? Because it was easier to consume. It was easier to use. So the use of technology increased. And we had a lot of reuse of common hardware that was out there. We also saw a decrease in CapEx cost and some operational costs because I didn't have to jump through as many hoops to spin up new instances. And I had one place where I could go and look and manage my whole data center with fewer operators. And cloud does not just mean public cloud. I have private clouds too, which leverage the same technologies and abstractions to do the work. It also gave me the ability to burst into the cloud, go beyond the capacity that I already had in my data center pretty seamlessly. All right, concerns with cloud technology? Oh, there's lots of concerns. Number one, security again. All of a sudden, my data is no longer in the safe walls of my data center or the perceived safe walls of my data center. It's now out in the cloud in someone else's data center connected to the internet. Oh, this is scary. Scary for a lot of organizations. And it paused. A lot of organizations would not move into the cloud and still haven't moved into the public cloud. They may have a private cloud. I hope that they do, because with a private cloud, I can see my security better. I can enforce security better. We also had another concern, which is noisy neighbor. All of a sudden, your applications are running on the same machines as other people's applications, and noisy neighbor becomes a big problem. Your performance predictability is now not 10% like I had with virtualization. Now, this is not performance degradation. This is performance predictability, which means sometimes it runs super fast and sometimes it runs slow because there's other things running there as well. Now, remember, the cloud service providers are all about squeezing every last penny out of their hardware. So they're going to run as many VMs as they possibly can within the performance SLA that they have given you, which is very sloppy at times. So you have to be concerned about that. There's also some integration costs that came up. How do I integrate with my private and public cloud? Egress costs, this little sneaky thing. How do I move data out of the public cloud into my private cloud or in between public clouds? That's very costly, right? It's measurable too, if you know how much data you're actually moving. We had a new change as well. And this new change in technology actually started before virtualization, but it was hard to use. It started way back in the 1990s with Sun OS, maybe even the late 1980s with containerization. People don't know this. Containerization actually started before virtualization, but it was hard to use. Not until Docker took this old technology and said, hey, this is valuable. Let's make it easy to use, easy to consume. And the whole concept of containerization said, we're going to abstract one more thing we're going to decouple the application from the VM. And we're going to make it so that my application can consist of containers, or my application can be in a container. And with it is my network configuration and my data that I need, or a volume of my data that I need. And I can describe that in a very simple, human-readable file that I can now deploy, and it can deploy across multiple VMs. I can deploy it several times. So I decoupled again, and I created this nice abstraction layer. And containerization now gave me yet another way of deploying applications quickly across multiple clouds, across multiple types of machines, and everything was nice and contained. This abstraction worked very well. Inside the abstractions, I have operating system, I have data abstraction in there, and I have a network abstraction in there, which drove software-defined networking. It drove vSAN, storage-defined networking. or software-defined storage, and also software-defined compute, all in a nice little package that I could deploy. Now, huge benefits to this: optimize OpEx. I decreased how much operational expense I had because it was easier for me to deploy. A developer could do this themselves without having a whole team setting up all your VMs for you. It could be done more easily. Decreasing my CapEx costs because containers have this lifecycle management around it. So now my application just isn't running all the time. I can specify how long this container runs, how many of the containers can run, increase my reliability because I could have fault tolerance built in, a whole bunch of really cool things. Much easier to integrate because there's a common language that I can describe these containers and how they connect to each other on these overlay networks, which is an abstraction on top of the software-defined networking. Concerns. Oh my goodness, security goes up again because now I actually have, in this container is highly portable and it can run anywhere. So, oh no, now I've got a major security concern because my application and data is now highly portable and can move anywhere. And the edge is starting to come in. So these can even run out on the edge, increasing my security attack surface. Also, something that happened, I would think that this would actually simplify things, but complexity arose as people said, hey, wait, my application can actually consist of multiple containers. And I can have multiple networks connected to my application. So all of a sudden, I had an increase in complexity, especially now because they're portable. They can now run across multiple different clouds and infrastructure and edge. And the big question that started coming up was, oh no, where's my data? My data? Well, a lot of the service management vendors like Docker, Kubernetes, which was open source that came out of Google, and a lot of people that have now taken those open source things and created their own things, their comment around data was, not my problem, data is available everywhere. Well, that is true if all your stuff is running in the cloud or even in your private cloud. But that is not true on the edge. And that is not true if you have any kind of data that needs separate governance or custom security around your data. Right? I can't have everyone accessing all the data all the time. That could be dangerous. So this becomes an issue. IoT is introduced. Of course, I already mentioned that. That just is spreading. Containerization made it so I could easily drop applications out on the edge. And now my data is all over the place. My applications are all over the place. Things are getting very, very complex. So how do I handle the problem of the data problem? Let's go back to our roots. Where did we start? We started with building applications for missions to transform data from one thing to something valuable. So let's go back and look at data. Well, I need to be concerned about data, like who has access to it, when they have access to it, and what it is creating, who has access to that. That's all data governance, right? That's very important. I also have, where is my data? And where is the information that's being generated? Is it at the right location? So locality becomes a problem. I can't say data exists everywhere because it doesn't. It actually resides somewhere. Now, there are some abstractions that we're talking about, which we'll talk about in a second, that make it look like it's everywhere. But locality matters, right? It does. I need to know where it is. Lifecycle management. Do I need to keep all my data? Right now, everyone's keeping everything. It's great for the storage vendors. Great for Intel. Great for everyone that's producing silicon. Hey, keep all your data because you might need to do something with it. But there's so much data we can't anymore. And the large amounts of data are just astronomical. Being generated on smart devices in your home, in factories, in smart cities, in aircraft, in vehicles. It's all over the place. So this is a problem that we have to deal with. Right now, people are just buying more hardware and software to help accelerate the deployment of new applications to work on this data, but we are leaving so much behind. And then how do I grow? How do I grow my business without understanding the data? Am I just lucky? We want to do a better job at understanding the data. So we got a big problem here. But there's some good news. In the last 5 or 6 years, we have seen the emergence. Well, we've seen the consolidation of the idea of data management, distributed data management. Now, I don't like to call it data management. I want to really call it information management. So I created this concept called distributed information management, which says that, but believe me, there's a lot of tools in this space already. But what I identified here was we need 3 major components or subsystems in this. We need data management, where I can move data. I know how to move data. I know how to life cycle data, to remove data. I know when to duplicate data, all that stuff. I also need a metadata management layer that tells me locality of data. It helps me with governance of data, who has access to what and when and where. And then I also need a data orchestration. I need something that can orchestrate when to move the data. And it needs to talk to the service management layer, right? Kubernetes and Docker, to know when those services are coming up and who needs the data when. And then I also need to work with the cloud technology or software-defined infrastructure layers, because they will be able to tell me what hardware is available and network connectivity is available, so I can move the data and where can I store the data. So today, the data orchestration, a lot of it happens ad hoc and manually, which is a nightmare when you're trying to deploy new applications quickly. So this is a really important aspect where, like I said, over the last 5 years, I've seen a lot of real startups moving in this space. Really cool things that are creating data meshes, global data networks, creating data meshes, creating federated learning models. They're taking a lot of the things that we've already been doing in data transformation technologies, in ETL engines and things like that, and now distributing them across in a orchestrated and governed way, which is super cool. It's going to be very cool, especially when I can start data orchestrating the edge too. As edge devices are becoming more intelligent, they have more capabilities, I can push more and more of my containers out to the edge, even running AI inference at the edge on very small, low-power devices. Super cool, right? Guess what this did? This increased my security concerns again, because now my data actually resides nowhere and everywhere at the same time. With these new data mesh architectures that are out there, the storage actually contains the data, but I can have multiple versions of the data and who's accessing the data. These are big concerns. And I need classification of data across these, because not all devices should be able to access the data because of the security profiles that they may have. Zero trust came into play. Zero trust principles have been around for a little bit, but they're actually old principles that we're re-evaluating again. And there's 2 major things that I've broken zero trust into. If you look and you've listened to the podcast, you know I have Embracing Zero Trust series going on, and we talk about the 6 pillars of zero trust. I broke those 6 pillars into 2 aspects: identity aspect and security aspect. Now, the identity aspect, when we talk about it, identity needs to apply at the application layer, at the data layer, at the container layer, at the virtual machine layer, and the device layer, all the way down to the device layer. Everything needs an identity. Everything needs access, authorize, and authenticate applied to it, so that I can marry hardware, virtualization, container, application, data, and person together, so that I can get the right data at the right time, converted on the right secure infrastructure, and given business or valuable information, actionable information, out to the right person at the right time. There's a lot going on there. It was so much simpler in the 70s, right? I had one machine, data came in, data came out, locked in my data center. People had access keys. It was easy. We're not there anymore. Those days are gone. And so we have to do more in this space. On the security aspect side of zero trust, I need to do a better job at detection, encrypting everything. I need good remediation. I need to establish hardware root of trust. And like I said before, there's a great series that's still running right now on the podcast called Embracing Zero Trust. You should check that out. Also, some news here. I'm going to also kick off in the next couple months Embracing Data Management. It is such an important and emerging field, and it will be the thing that really enables AI and generative AI to be useful in business in a profound way. So we got to work on the fundamental blocking and tackling on data management. So look for that series coming up. If I boil all of what I've talked about today down into something, we have created something called the Edgemere architectural concept. And what we've taken is we've taken that simple thing that we've learned over the years of taking data, applying an application to it, and generating information. And we've identified the different layers that exist today, where I've got distribution of data, applications. I've got software-defined infrastructure. I got physical layer. I have security all in here. This architecture helps us understand how all these pieces fit together so I can get back to the type of security and the type of information that I was getting before, right? In the early days where my data came in a machine and information came out. Now we're trying to capture all the data that's being generated and give you actionable business information coming out. Thank you for listening to Embracing Digital Transformation today. If you enjoyed our podcast, give it 5 stars on your favorite podcasting site or YouTube channel. You can find out more information about Embracing Digital Transformation at embracingdigital.org. Until next time, go out and embrace the digital revolution.